Thanks, Francesca.
Here you go.
Thanks, everybody. Yes. Okay, thanks. Okay, so I'm Mike Douglas. I'm going to talk about, I decided to give a fairly broad survey of things I've been working on, things even projects that are progressing slowly, but that I think are very important. As you can see, some of them, three directly relate to our proposal and appear in the proposal, and others not clear, but I hope you'll find them all interesting. And I believe there are many potential connections to make. Okay, so I'll just say also a few words about myself to start. I think one of the things I bring to the collaboration is a great number of connections and knowledge. And so where does that come from? Well, as many of you know, I spent a lot of my career doing string theory. And I left academia in 2012 for a variety of reasons and worked at Renaissance Technologies for 8 years. And I had followed machine learning and AI actually since graduate school, but this, among other things, gave me quite a bit of practical experience of what is it really involved in getting something to work. And so I was doing that happily. And meanwhile, deep learning, of course, took off about that same time. And in 2016, many people, including me, were convinced that this is now going to be the golden age of machine learning and AI. AlphaGo had clearly broken new ground, and so I gradually shifted into what I'm doing now, which is basically a broad focus on AI for science. How can you use AI to help do the many kinds of science we can do, and I'm doing that at the CMSA, which is a multidisciplinary institute. So it's not just mathematical sciences, but all ways that mathematical sciences could make contact with science, and so very appropriate for this sort of activity. And it's been a great opportunity to follow a lot of the cutting edge research. That's, many of you know about our seminar series, the program we just held and so forth. So, okay. So let me go through some of these areas. Okay, so one of the things I've been doing for the past 5 years is machine learning for most specifically questions like approximating Calabi-Yau metrics, but a variety of things and what's called geometric PDE. I'll give a few more examples. And again, this is clearly applicable to many areas of science. And if we had to say one thing which makes this possible beyond, of course, the huge improvements of computers and software and GPUs and the rest, it's that feed-forward networks and other machine learning models can beat the curse of dimensionality, and so you can treat higher dimensional problems, and in fact, very high dimensional problems if one wants. And then the most straightforward way to do that would be to just minimize the a loss, which is your distance from solving the equation, and that often works. And so in about 2020, several groups, including a group I started, have been doing this for Ricci flat Kähler metrics and Calabi-Yau manifolds. And again, I want to give more of a survey. So those of you who know what those are in detail, that's great. And those of you who don't, it's there's a concrete equation in terms of one real function on the manifold, this Kähler potential, and you're basically minimizing the error with which you solve that equation. And this works pretty well. This works. There were such results in the past, but with previous computer technology, you basically needed very large amounts of symmetry because the standard physics problem is in 6 dimensions, which is pretty high for PDE. And with neural networks, a laptop with a GPU, no problem. Okay, so what are we doing with that? And that has largely been in collaboration with mathematicians in my case, although there are well-known physics applications that involve string compactification, calculating Yukawa couplings, this sort of thing. My own work has been more to solve problems of interest to mathematics. So for example, construction of a G2 holonomy metric in 7 dimensions, and with an eye on results that could be rigorous. So in this particular paper, you can find online our results not rigorous, but there's a clear path if you wanted to make that one rigorous. And then there's a range of these kind of problems where there's not like a very clear technique for getting at it, and so numerical methods are good for exploration and potentially teach you something. And so famous question that I think about is complex structure on the 6th sphere. Again, some of you will know this question. It's not clear that it's ripe for machine learning yet, but it could be. We looked a bit into the question of whether there's a Ritchie flat metric on the product of 2 spheres. The main thing in this direction I'm doing at the moment with a fairly large group of mathematicians and also Yi-Di Chi, Jim Halverson's postdoc at Northeastern, who was part of many of these collaborations, is to rigorously prove that a Calabi-Yau metric, a Ritchie flat Kähler metric exists. And so in some sense, the whole foundation of this field is Yau's famous theorem. Let me move on a bit here, that these metrics exist, and that's why they're called Calabi-Yau metrics. And so this was back in the 70s. And, again, it's an important topic in mathematics and, extremely technical and very difficult to generalize to other similar equations. So from the string theory point of view, there are a lot of maybe 10 or 20 classes of equations like that. There's one called the Holstrom integer system, and there's various things coming from the various string theories and M theories. And you would like to have the analog of Yau's proof for all these things. Under such and such conditions, you can solve the equations and get a string compactification. And then Yau and others have been working on that for the past 40 years. And it's difficult. And why is it difficult? And again, not to go into great detail, the structure of Yau's proof is that if you can know something about the solution, something about the norms, that the curvature is not too big, that the derivatives are not too big, then you can use mathematical techniques to analyze this equation. But if you don't know the solution exists, how do you know anything about these quantities? And so this is what's called an a priori estimate. And this is very difficult to get, as you could imagine, if you a priori don't know much. And the new, basically, technique is to replace those a priori estimates, which is computing the required numbers from the numerical solution. And so this is, again, briefly outlining for those who are interested. I could give a longer talk about this, but rather than the style of Yau's argument, if you know it, there's a very general class of arguments that use what are called fixed point theorems, where you rewrite the equation as something phi, in this case, this Kähler potential, is some known functional of phi. So, clearly, if there's anything that looks like phi in the equation, you can do that rewriting. And then a fixed point of that equation will be a solution of the equation. And then there are these very general fixed point theorems that tell you, what are the conditions on f and phi that you need to prove that a fixed point near some point exists. You can imagine if the error of this is not too big, then you could prove that nearby there really has to be some fixed point. And so that gives you the list of the quantities you have to compute. And then how can you turn a numerical thing into a actual rigorous proof? Well, there's this subject of a verified numerics, where instead of interpreting your results as numbers, you interpret them as bounds. You say, I'm going to always make sure that my rounding, my other errors, round down, say, and then I can say, well, at least I have a lower bound for the actual solution of my equation. And so if you're very careful, you can get rigorous bounds out of your numerical calculations. So it's combining these ingredients, and kind of technical, but I think we'll have a big impact on the subject once we can get through an example such as this Calabi-Yau one. Questions? People are there?
Yes, I have a question. So how much of this kind of proofs relies on, say, the structure of Calabi-Yau, and how general can this be made?
No, this
set
is
of
very
proofs?
general. These techniques have been most used for Navier-Stokes and simplifications of Navier-Stokes, which are very different than PDEs. And so that's the attraction of it, is that it's a very general technique. Other question? Yeah, I mean, PDs come out of all, any of the things we work on, and if one's interested in rigorously proving solutions, this is potentially a powerful technique. Okay, so let me move to the next topic, which is economics, and this is partly again my experience at Rentec gave me some familiarity with some questions of economics. I'm not certainly an expert, but I was able to work with an expert, a postdoc here at the CSMSA named Sergei Verstyuk. And so we have a few papers. They're mostly on this archive called SSRN. The economists and social scientists prefer that, but we did actually put our most recent work, and it just appeared today on our archive, the econ topics. And so one of these papers, which relates to potentially, distantly, but I think is very interesting, is to do a multi-agent simulation of an economic model where we replace the usual mathematical optimization that defines the actions of the agents with large language models. And so there's many of these models out there. We studied a particular model of the business cycle, which again had been studied in depth in the economics literature for maybe 20 years, and it's a model of the business cycle, and it's a lot of things in economics are idealized. So there are many agents. There's a firm that they work for. There's like a weak and a strong state of the economy, and there's lots of jobs for everybody if it's strong. There's not so many jobs if it's weak, and then this is basically a two-state Markov process. It just kind of switches back and forth in an unpredictable way, but you can in principle infer the probabilities with which it will switch. So there is that kind of structure in the problem, and so the agents now are, if they're, sometimes they're jobs and they can work, they earn money, they can consume, and they gain utility, and that's their goal that they're trying to maximize. But they can also save money to, cover the potential, future loss of employment and this sort of thing. And, so the kind of question you can ask is, well, here's all these agents responding, to, the ups and downs of the economy, and do their responses tend to amplify the effect of some sort of shock, that affects the economy in a good or bad way? Does this amplify it or damp it? And it can do both, actually, depending on the situation.
So Mike, sorry, can I ask just a question about the setup?
Yeah.
When they interact in their LLMs, are they just they're using natural language to interact?
I'll say that on the next page. Exactly.
Okay. My question is going to be: Are they lying to each other deliberately, or does any of that?
That's a good question. Okay, that's right. So indeed, I'm going to say a little bit about what they actually do. Right. Okay. Just to finish the general description of the model, again, there's this list of questions that you study, and another one would be that we have this, maybe there might be 100 agents in a simulation, so they start off roughly equal. Does inequality grow with time? That would be a kind of question that you would ask. And so now again, what did we do? Well, we do pose the economic situation to the agents and ask them to make their decisions all in the natural language. And I didn't put a detailed slide, but you can see this in our paper. And it's pretty long. You have to say, we give them like 10 cycles. A cycle is supposed to be like a quarter or something, 10 time periods of economic data of, what did you do in the past? What was the economy like? What was the general, what were the prices of things, which is how in the standard model, the way the agents, they don't directly communicate. They communicate through the market, that, the more workers there are, the lower the wages could be, there's a price of something. And so anyways, we give them this data, we describe the problem, and we tried a variety of things. We tried both describing it in very economics terms, and we tried describing it in more kind of standard, informal natural language. And it turns out that, and it did require, it only became possible basically last year, both because the prompt is maybe 10,000 tokens long, so it was really running up against the size of the GPT window at that point, although they then increased the window and that became less of a problem. But of course, the other problem is that this does require some ability to do, word problem solving and logical reasoning. Now, it doesn't require a great ability for a variety of reasons, because we can do several trials at a problem, and we can only keep the answer which looks like the most sensible one. We can judge it a posteriori, and also, the whole point is that they're not supposed to be perfect. They're supposed to be more like humans. So as long as the answers they give actually make sense in the context of the problem, they don't have to be the true answers or optimal answers to the problem. And so that's the outline of what we did, with software to obviously take text from one agent and send it to evaluate, pick out the values of the fields, evaluate it, and so forth. And then there were a couple of versions of this, and one of them we also allowed them to communicate with each other in natural language. Okay, and so that's the point where the sort of question that you ask, Eva, do they tell the truth? Do they lie? Well, that's a good question. I mean, it would be even more work. I mean, we did some analysis of the actual content of their communications, and it was more to address this last question. Okay, so again, another standard question you could ask is, try to figure out what do the agents actually understand of the situation. Like, for example, are they actually estimating the probability of the economy switching between the strong state and the weak state and so forth, and are they doing that correctly? And you can ask them. That's the way that we try to do that. And
Michael, can I ask a question? I mean, those LLMs, you give them a goal.
Yeah. The goal is to optimize.
But in which sense?
The utility. Yeah.
In which sense? Because you ask them to have a goal.
Yeah. We tell them, and we try.
In which sense would they? Let me ask the question. In which sense would they pursue the goals that you're asking them, or just fake the fact that they are pursuing a goal, right?
I think that's a good question. So we tried different things, and there was a more kind of closer to the economics version where we define the goal as the discounted total consumption. And there were looser things where we said, you're just trying to maximize your utility. And I think the honest answer from what I looked at the answers is that they make some effort. They have some understanding of the utility, but they do not understand it as the actual equation, the discounted total consumption. And so I think the answer is sort of in between. I think, again, this is not like, I would not hold this out as a very, very, good simulation of economic behavior. I would hold this out as an interesting example of what you can do with the present technology. And then, of course, as time goes on, they'll get better. You explain the problem in more detail, and they will more closely adhere to the statements of the problem. But yeah, they're not ignoring the goal. You can judge how well they're solving it and whether what they say corresponds to in any way to trying to solve the goal. And basically, again, the simple goal here is they get to decide how much of what they earn do they spend. And it's good to spend more. So at that level, the goal is pretty clear, and they are following it. Now the question of, well, are they discounting future utility in the way that we're proposing? Well, probably not. But so does that answer the question?
Yes, thank you.
Yeah. Okay. So anyways,
Michael, I had a question. Can you get these boom and bust cycles without any time varying exogenous drive?
I think you can. That's right. I mean, this is again, it's a big field, and for sure you can. I mean,
And related, I put a note in the chat. There's an interesting AI startup called Altera.ai that created a community of agents in Minecraft that interact with each other.
right.
And the society developed all sorts of interesting emergent behaviors, including cooperation and deception and stuff like that. You can actually see videos of the demo by going.
Cool. Yeah, cool. I'll take a look at that. So yeah, that's right. I mean, this is just the tip of the iceberg in terms of looking at the economic models. And this is an example showing, again, the sort of things that the agents generate. And, then part of it, we extract out some of these numbers and feed them into the actual, model, of, what happens for the next cycle. And part of it is just, actual natural language communications between the agents to see if they can influence each other in some way. And, then here's, some examples of consumption versus income, So in general, obviously, if you make more money, you will spend more money. And then the blue, the straight lines are the solution of the model using mathematical optimization. And it's not an easy thing because, I mean, if you really try to, all the agents try to model everybody else, then it's intractable. So you make some approximations, and that's why there's two lines there. And then the blue is data for this language model simulation without communication, and the red is with communication. And it's very clear that again they trend up. They do consume more when they get more income. They if they're unemployed, they do save more when they're unemployed, in the expectation that you're going to need to, they may need it later. And there's a statistical, though I wouldn't say hugely convincing, difference between the with and the without communication. And one of the basic things that's going on here is that they seem to save more than the optimal amounts. They're below these lines. They're consuming less, and especially they do that when they're unemployed. And the communication to each other seems to be encouraging them to do that. And
sorry, Mike, were they endowed with basic needs? I forget what you said about
no,
that.
so it's an abstract thing where there's like one number of how much do you spend each period, and then the utility is basically that, and then the standard thing would be to have some discount rate to say you try to judge the future utility, but then you discount it in your optimization.
Okay, so okay.
But there's just that one number. How much do you spend? And you're just trying to, consumption, and you're just trying to maximize it in some sense.
Okay, gotcha. Thanks.
Very, very idealized. And, then you can study things like, well, here they were put in this environment and we gave them these histories, that was where all their memory is in these histories and inside the prompt each time. And so, what do they actually understand anything about, probabilities, about, the, structure of the environment, and they do, again, they definitely understand something, and it's not the the obvious kind of mathematical estimate of a probability. It's something that focuses more on the recent events, and in that sense, it's more like a human expectation. So we were quite pleased with it in terms of again, like a initial study using these techniques to address really traditional economics questions. Are there questions about that? Okay, so here's the work that we finished a while ago, but we just put it on the archive, which is an actual interesting contact with scaling laws and with the progress of AI. And okay, so we got scaling laws, and we're all familiar with that. We look at some measure of performance as a function of model size, data set size, compute, and so forth, and we get these scaling exponents. And again, what my collaborator noticed and taught me is that there's a much older tradition of doing this sort of thing in economics. And in fact, amusingly, like the original paper is called the Cobb-Douglas production function, which no relation to me, but you can ask this very general question of you have various input factors which you quantify, and capital and labor. How much do you spend on payroll? How much do you spend on machinery and stuff? And then how does the amount of output that a firm can produce depend on these things? And so you start with some very simple ansatz. Of course, economists are like physicists in that sense. They don't want to. They just want the simplest model that captures the qualitative phenomenon. And this Cobb-Douglas production function just depends on the single exponent alpha. Very generally, you can argue, and empirically, often turns out that there's some power alpha, and the output is proportional to the capital to that alpha, the labor to the one minus alpha. And then this is something where it scales in a linear way for obvious reasons. And then we, again, mostly, Sergey did a very detailed empirical study. Okay, and so what is this graph? Okay, so what would you, traditionally, how would you have judged progress in some field? Well, what are the outputs? Well, there are papers. You can count the number of papers people write. You can count the number of patents people write. And this is a log scale. And this is the year. Okay, but now that we have the computer, we can quantify things. Now, another older scheme for quantifying is available in competitive games such as chess. There's the famous ELO scale, and it turns out that it makes sense to put the ELO scale on the same. You can think about its definition, and you realize that makes sense. And then there's data going back to the 80s of computer chess. And that's these green dots, the advance of the ELO scale. And then more recently, of course, we have benchmark sites. We have like papers with code, and we have other systematic benchmark sites. So we have things like the ImageNet is the blue, and some particular language model is the purple. And then one of the main contributions to this is to say, well, any given benchmark, of course, is going to saturate. But maybe we can make some sort of an index, which is kind of like the Dow Jones or the S&P 500 and so forth, which has a very fixed rule for incorporating new benchmarks as they come out and dropping the old benchmarks as they become less relevant. And so there's a very specific definition. We explored some possibilities, and there's such a definition, and we call it the ASOTA, AI State-of-the-Art Index, and that's these red dots. And of course, in this, it kind of fits with all the other things. There's not that much difference, but that's a number that could, in principle, be continued indefinitely into the future. Okay, so those all represent this Y, these measures of output, and they're all growing on exponentially. This is a log linear plot, and so then you can say, okay, well, suppose we just try to model it with this. We got capital. What's capital for compute? Well, it could be the actual amount of compute that you have available. I mean, it could be dollars, but the much bigger effect, of course, is not the dollars. It's the Moore's law, which says that the cost of computing has gone up at this outrageous, exponential rate, doubling every 2 years. So that's really the more appropriate definition of K in this thing, is the amount of compute that you have. And then, well, this function also depends on labor. Why not put that in? It's a secondary factor, but certainly there are more people working on computing and AI than there were in the past. And then there's a very interesting way you can use that, which I'll get to momentarily. But before I say that, let me just say that if you take alpha to be 0.2, okay, you get these black dots, and you substitute in, Moore's law, and then the actual, computing resources times Moore's law for how many flops you get, and computer science payrolls, you get these black dots, and again, it kind of matches pretty well this orange and blue lines. And they really are kind of doubling every 10 years, which is this 0.2 exponent. And then they're not totally off of the computer, the ELO, the AI benchmark progress. But I would say this one is more kind of like alpha equals 0.5 or 0.6. It doubles every maybe 3 years or something like that. So it's slower than Moore's law, but pretty fast. Okay, now there's this, and what I found quite striking, independent way of getting this 0.2. Okay, and so this is in the paper where you can say, suppose your firm is trying to maximize its output, then there's a short argument that says that whatever profit it gets, it should spend fraction alpha of it on increasing its capital, and fraction 1 minus alpha of it on increasing its labor. In other words, it's a payroll, and it's kind of an obvious thing you can imagine if you just compute the optimum, and then you can say, well, what fraction do research companies actually spend on payroll? Well, that's payroll data. That is a very big data set on that, and it turns out it's like 0.8. It's actually quite a bit higher than generic kind of firms. It's like 0.6 or 0.7, and so amusingly enough, that leads to this spending capital up to, to the 0.2. And so it leads to this 0.2 in this law, totally independent, before you even plot this graph at all. And so that's where these black dots come from. And so in that sense, there's like a no parameter that predicted this growth. And again, not totally off with this growth, but I think, there's something else going on here, perhaps improvements in algorithmic efficiency or perhaps something else. I mean, another interesting observation, there are a lot of, I recommend the paper. So there's this, classic idea of the AI winter, which certainly affected, the researchers in the field very much. But if you look at it, if you step back and look at the bigger picture, there's not such a concept of an AI winter. It seems like the progress is really much smoother than you might have thought. Okay, so I'll stop there. Questions about this? Should I move on?
Well, do you have a theory for why all these curves look so similar across so many domains?
Well, yeah. I mean, obviously, it's showing that there is something universal about progress in this field. I mean, that's a theoretical hypothesis. Now how deeper can the theory be? I mean, it is very striking that the slope of the green line kind of matches up with the AI line, and again, it's not Moore's law. It's noticeably different from Moore's law. It's somewhat slower, although not hugely slower. So indeed, I think we should push on this. My collaborator actually is a little, embarrassed isn't quite the word, but he feels that economists don't appreciate this sort of work enough. But I think this is great. I think there's really some things to understand here. Okay.
Sorry, so these other measures are rising at a faster slope than Moore's law? Which
No,
one
no,
is
slower. We didn't put
slower?
Moore's law, but they're rising. So this exponent is comparing basically with Moore's law. It's saying, compare, it's if Moore's law is doubling every 2 years, then this doubles every 2 over alpha years. And so for 0.2, it would be every 10 years. And then in practice, these things are doubling every like 3 years or something. So it's like 0.6.
I see. So we're not exploiting Moore's law as well as we could be? Is that
Exactly, that's right. There's other factors in it. It's not just Moore's law. That's maybe the biggest takeaway from this. That's right. You might have
there's other factors that are
run it. It's
impeding
very
us?
clear, and it's very clear for the papers and patents. And then there you might say, well, obviously there has to be a human input, at least at the stage of the art, and then that's modeled by this.
I see.
Yeah. So yeah.
So why are the exponents alpha and 1 minus alpha? Why can't they be independent?
Well, in principle, here they can because it's not a material thing that we're creating. I mean, if you're creating material things, then pretty much you have 2 factories, you make twice as much, or 2 firms. I mean, there's much more sophisticated ways of putting that argument, but then that's the basic intuition, is that in many circumstances there is a strong reason why production ultimately is linear in the combination if you scale up all the factors. But I agree, for a non-material thing, that's an assumption, and I'm not sure we would be strong enough to directly test it. But again, this is sort of a test for the papers and patents thing. The fact that the 0.8 is coming from totally independent data, and then it leads to this 0.2, which does fit. So we do have an empirical confirmation of it for that case. But yeah, no, I wouldn't say it's many more questions than answers.
What's the green again?
The green is the data on the best computer chess programs ELO score from some Swiss computer chess club who've been keeping track for a long time, and is widely considered to have the best data set. There's some reason why it suddenly jumps in 2008, which I think they know, but in general, it also is a surprisingly constant exponential growth. Okay. Shall I go on? More to discuss here? I mean, I guess I'll go on. Okay, so now we get to topic 3, and what is this structure in data which allows it to be learned? And then there's a question which I put in the proposal last year, and which I like. I think again, it's an example of something that we could work on. Let's look at MNIST. Well, MNIST obviously has structure; it gets learned. But now, of course, you can step back and ask, where did the structure come from? It's true; it's just an empirical data set, but it was created from something. A million years ago, these digits did not exist, and there was a process in the meantime that created these digits. And you can idealize this process, and you can think of a writing system. It clearly is a communication channel where you're starting with a digit as a tenfold choice, and it proceeds through this process of writing to produce an image, and some reader that converts it back into a digit. And there is an optimization of both the accuracy with which you can read the digits, the speed, the difficulty of doing the writing, maybe the time it takes, and so forth. And there has to be that a good part of that evolutionary process that again, it's not like these are the only possible digits, but they should be some local, somewhat optimum within the space of possible writing systems. And you could imagine producing that one, with the right contingencies happening along the way. Or you can imagine producing other systems of digits. And so by developing this idea, you can come up with a simulation that you can use to study the evolution of, for example, writing systems. And I've looked, it seems like such an obvious idea. Somebody must have done this in the past, and I wouldn't be at all surprised, but I didn't found it. I found ideas, ideas that are in this space in the literature, but I haven't not found this project actually carried out. Okay, so let me move on, because that's just a proposal. And now ask the question which Surya encouraged me to think about for the current proposal. What structure in a search problem allows learning to solve it? And well, again, this is like a classic, very classic computer science question. Search is like one of the core topics of traditional AI. And now it becomes topical again because reasoning involves search. What's a ideal form of reasoning is to solve the SAT problem. You're given a list of Boolean expressions, and you're looking for a satisfying assignment. And it's a bit oversimplified, but basically the statement is you just got to search through the possible assignments. It's NP hard. There isn't any fundamentally faster way to do it. It involves search. Okay. So what can we say about that? Well, quite a lot has been said about that from statistical physics methods. And much of it, certainly the things I'm most familiar with, look at the distribution of a random K-SAT and constraint satisfaction problems. And so I think very important things have been learned, but I think it's also, and certainly in my experience, when you tell actual computer scientists about this, they kind of roll their eyes and say, these random problems don't really have that much to do with the problems that we actually solve, And so, well, it's because they have structure. So we want to do the same kind of thing we're doing for the data. We want to postulate search problems that have structure and understand what allows to, to be solved. Okay, and so I'll say some things about that. Are we going to have a hard cutoff at 1? Should I start skipping things, or should I just go at this speed?
Can I ask a question?
Yeah, please.
I usually don't think of search and learning together, really.
No,
so
they are not the same thing, but you can think of them together. There is
is there like a more concrete example where there is structure and then learning can successfully carry out the search somehow?
Yeah, that's what I'm going to describe. I'm going to talk about
okay.
learning to solve the Rubik's Cube.
Okay.
Yeah. Does that qualify?
Yeah,
Okay. Yeah. Okay. So right. Okay. So this is maybe I'll skip this because it's not my own work, but I think it is a very important paper to point out, which is Pan et al., which actually do both train a transformer, not an LLM, but a transformer to solve SAT by search, by generating a trace. It's an autoregressive, transformer, and show that there is some set of weights which really would do that, as well as doing the empirical study of how can the thing learn to do that. So to my mind, that's in terms of the problems of search and reasoning that you can actually analyze theoretically. This to me is the state of the art. I mean, of course, there can be other things, but I think this is an important paper. Okay. So this is now some classes of search problems that we might try to look through for interesting, again, families of problems that have structure that can be learned to be solved. But the one that I'm going to focus on is this problem of learning to find paths in Cayley graphs. Okay, so we have a group G, we have some subset of generators S in the group, and so as I'm sure everybody knows, you have a graph where the elements are the vertices, and if you can go from one element to another by applying a generator A, then you put an edge between them, and then you can ask, given two nodes, is there, what's a path or what's a short path between them? And of course, because it's a group, you can always reduce that to the case of is there a path to the identity? And then one nice thing about this problem is that you can explain it to everybody, because the problem of solving the Rubik's Cube is an example of this, again, is probably evident to everybody. But what's not totally obvious, but which is true, is that the set of configurations of the Rubik's Cube actually is, in this case, isomorphic to the set of elements of the symmetry group of the Rubik's Cube, of the group generated by the operation. And that's basically because every operation does affect the state. There aren't like fixed, did X faithfully. Okay, so that's, again, not like, sad, but it is a problem that has certainly attracted attention. And back in, I guess 2018, this was a question. Well, if your reinforcement learning is so good, can it learn to solve the Rubik's Cube? And this was this challenge was met by Mackley or Agostinelli et al. In 2018, 2019. It was very nice work. And then the attractive thing in terms of trying to find problems with structure, of course, is that what could have more structure than this? This is like a class of problems, not necessarily the Rubik's Cube itself, but for general groups, general Cayley graphs, is connected to a huge amount of deep mathematics. It's a very open and vibrant thing. We had a lot of discussions about it in our math machine learning program with Jordan Ellenberg and other mathematicians. And there were many conjectures, this famous Andrews-Curtis conjecture that physicists have worked on recently can be considered an example of this. It's a little different, but it's definitely within the same paradigm. You can make a group action of the Andrews-Curtis moves. And then there are many other interesting math conjectures and theorems that relate to this. And so the kind of example that you would start out with there is, let's take the group of 2x2 matrices of unit determinants where the entries might be integers, they might be out of a finite field, and then we'll take the generators to be 1, 1, 0, 1, 1, 0, 1, 1, or maybe we'll take n instead of 1, and so then that's in itself an interesting studied problem, and the maximum, of course, the length of the path will be the diameter, and again that's much studied, but there actually isn't an algorithm that's known that finds paths of ordered diameter. In fact, this paper even provides a non-deterministic item. So again, it's an open question of interest to mathematicians and I would hope physicists. Okay,
Mike,
so
couldn't you try to solve these problems using diffusion models where the denoising process is diffusion on the group?
Okay.
And reverse. And actually, there's a lot known, right, about diffusion on the groups. And
for sure.
I
That's
think
right.
they're eigenfunctions at your reps.
Exactly. That's why I advanced to the next slide. Exactly. So Kit Fraser Talenti is a student who attended our program and is had exactly that idea, because so where does that idea come from? Okay, so the training set that one typically uses in this is a series of random walks. You start from the identity. So what do you, I mean, basically just to so suppose you could learn the distance of a group element to the identity, okay? And you could have a neural network that learns that. Well, that would solve the problem because of course, for any given group element, you would look at all its neighbors and decrease the distance to get the policy. And then how do people learn that? Well, the standard thing, is that doesn't assume any structure or non-knowledge of the group, is to just start doing random walks starting from the identity. You go for T generators, you get to G, and then you use T as your estimate of L, and you learn that. And so you've generated the data, the initial data through this forward diffusion process, if you like, discrete diffusion. Now, of course, you might quibble that T is actually not L because it's diffusion, although it depends what kind of group you have, but again, if T is monotonic in L, then you're just as good in terms of defining this policy. And so at that point, and another inspiring paper for us, Takano used the probability that you generate a particular group element from the random walks, which would be a related quantity. I guess now we're getting even closer. And then, in some sense, the machine learning content, and of course, there is this reinforcement learning search aspect to it, but then there's the question of, well, can your network or your function class actually represent V of G? And of course, that depends on the features that you use to represent G. And so there's, a fair amount to say there as well. Okay, so yes, that we think it is fruitful to think of this as a diffusion model. So the data generation process where you start from the identity into the random walks is a forward diffusion. And now you're trying to reverse that and get back to the identity in this case. In this case, there's one starting point, though you could generalize the problem. And so there's, basically we postulate the forward process. You might have, uniform probability to take, each choice going forward. And then there's some score function, which is the basically, ratio between, this and the reverse diffusion, that exactly reverse this probability distribution. And if you knew that, you could get back to P at time 0 is concentrated on the identity. Okay, so then, we did that. Kit essentially did that, and you can postulate a divergence. In this case, it's a Bregman divergence between the score function and this ratio of probabilities. And then, of course, the probabilities you estimate empirically, and so you get a loss function that depends on sampling over the path that you generate. And then that's learning this network sigma, which approximates, learns to approximate the score function. Okay, so that works. And then although again we're really more in the beginning of doing this, but one possibility that this opens up, of course, is that instead of just having uniform random walks, why not also train the forward process to optimize how you explore this Cayley graph? So that now becomes a possibility. You can also vary the forward drift term. And then there's kind of a simple prescription where you say, well, we already got a score function. Let's try using the score function also in the forward drift term, and kind of co-train these things, but use the same score. And that turns out not to be a stupid thing to do, because if you look at that score function, you can call it, in a sense, a normalized inverse of the probabilities. You take the probability that you've explored in some direction, and roughly it's 1 over that normalized to be a probability, so that it does favor exploring the directions that you haven't looked at already. And in any case, you can try it. And again, our starting point was fairly similar to this work of Takano, which is the so-called efficient cube on this plot. And we get pretty similar results to Takano, which did better than McEllier and Agostino's work, Deep Cube A. But ours does it with 20 times fewer samples, so 100 million trajectories instead of 2 billion trajectories for the same performance. So there's clearly something there, and we're looking into that. Okay, so I'm again fitting it within our larger context as an example of search problems with learnable structure, and then I also intend to think about and have thought in the past about broader classes of problems with learnable structure, and they tend to come out of logic. Again, if you ask, the usual sort of thing, like a family of groups or like a family of optimization problems, there's usually, the interesting ones tend to be ones that have some kind of more concise mathematical definition of the family of problems than the individual problems, and that again, there's quite a bit known in logic and theorem proving about how to generate such classes of problems. So there may be something, concrete ideas that are interesting for us there. Okay, so I don't have a lot of time for topic 4, and it's just as well because, again, it's a thing I think about quite a bit and discuss in particular with David McAllister, whose work I'll describe a bit, and I think is very inspiring in the sense, and what's the basic point here? Okay, the point is that we're using, as scientists, computers, AI to help us make discoveries. But I think if you ask, has a computer actually discovered anything by itself? The honest answer is basically no. And again, I have a much longer talk that goes into just debating this kind of question. But then you can ask, well, so what would qualify as a discovery? Just because the computer's computing something which you can interpret as a proof that such and such object exists, does that mean it discovered it? Well, obviously not. We don't say that the computer discovered this solution to a PDE or whatever problem it solved. We said it solved it. And so what is discovery? And I think, again, you could make the answer, and I think the standard answer is to say, well, the system has to have AGI, has to interact with us and convince us that it understood that it made a discovery, and that could be that's the answer. But I think there are answers with much more internal structure that don't, in principle, require AGI, and there is again a small but interesting literature on this. So there were the symbolic AI systems for math discovery back, especially in the 90s, and this still goes on, that generate databases of interesting mathematical objects and conjectures, and which did attract attention. Those, of course, were symbolic. They tend to require a lot of hand coding and not scale. They run out of steam. Okay, so here's a few current approaches to this sort of thing. Okay, so David McAllister, again, computer scientist at TTIC, created one of the first AI math systems, and he has a proposal that he calls Math Zero, which is very general. It discovers concepts which are described as what are called signature axiom class. So it's basically what you would see in Bourbaki. A group is a set, these group elements, a function, the multiplication, maybe another function, the inverse, and then these axioms and so forth. And so it's that kind of a model. And so the goal is to discover such signature axiom classes, which he would identify with concepts. And so, for example, give it sets, could it discover the natural numbers as the cardinality of the set? And he would argue yes, and is trying to develop a system that would do that. But it discovers all sorts of stuff, and ultimately, to make, the problem with this is not that it can't work. The problem is you get this huge number or list of things, which is far greater than what any human would count as a discovery. So somehow it has to filter out the interesting ones, and that's not clear how to do. Another very interesting work, very recent, this is Noah Goodman's group at Stanford, Gabriel Poesia and collaborators, is what that system they call a Mimino, and this builds on an older concept of intrinsic motivation, that you can add reward terms to reinforcement learning systems for other purposes than just the extrinsic reward. So, like, for example, the process reward model in current LLM training. And so again, I think this is an interesting paper if you want to get into this field. They have something that generates conjectures and then generates proofs using a language model that they train on this database of conjectures and proofs, and then they feed it to a verifier that they developed called Piano. There's this idea of hindsight relabeling, that many things are just too hard to prove, but whatever you were able to prove, that's a partial result. You could say, well, at least I did prove that. Now I can train on that pair of proof result. And then kind of the interesting point where it gets into, well, interestingness is to say, now we want to choose proofs of the appropriate level of difficulty to train the language model on going forward. We don't want it to, train on a lot of very easy or very hard things. So they evaluate the likelihood of the proof in terms of the language model probability, the probability that such and such a proof would be generated, and then that gets identified. The more likely the proof, the easier it is, and so that they're able to select that way. So I think that's an instructive paper in this field. Okay, so you can also kind of step back and really try to write objective functions for what's an interesting discovery. And this kind of builds on this, circa 2000 literature about where they use heuristics to identify interestingness. Now we would say, well, so what is the objective function? We just want to optimize it. And so here's an example of how this would go. So like, is a proof or a theorem useful? Okay, well, here's a concrete definition. Okay, so L of S is the length of the proof of the statement S that we're trying to evaluate. And basically what we want to know is for the statements that now might arise that we're trying to prove, is the length of the proof given that you know S shorter than what it costs you, the length of adding the proof S to the database. Okay, so this would be the usefulness of S. If S generally shortens the length of other useful proofs, then it's useful. And so it's sort of in the spirit of Kolmogorov complexity. And, that's up to the, well, I mean, that's perfectly well defined. The problem is that, well, what are the statements X that we want to evaluate this over? And that's where the difficulties come in. You can evaluate it over the statements you already know. And that is utility. But what you're also generally interested in is some sort of a interestingness of, do I think S is worth proving to prove new statements? Okay, and then you have to somehow estimate this. You would probably train your estimator on utility and change it in some way to represent this interestingness. So that's an example of this kind of question.
Mike, has this appeared in the literature, or is this your
Things like this have. This idea is sufficiently obvious that other people have had it. I could tell you references, but nobody's developed it systematically.
And has anyone implemented it in any concrete situation?
No. The references I know did not implement this. I mean, the basic problem with the research in this field, I would say, is that until your verifier reaches a certain level of, reliability of sound, able to actually prove, verify proofs, and your prover has, some ability, then it's very hard to do any of this research at all. And we're just now getting to that point. So like this paper does implement everything they talk about, but it only proves very simple conjectures, like simple statements based on the axioms of group theory and logic and so forth. And that's basically because of both, the language model is not a big language model, and their language of their prover is kind of primitive. So I think these are the things that come after that. As that advances, this starts to become interesting. But I would quite agree that it's worth, as this group, of coming up with simpler problems of this sort. And this is a project we could do. We could implement this in a sufficiently simple thing, not strong enough to derive really interesting mathematics, but strong enough to show that this makes sense. Yes, that's why I presented to you as something we could work on. Okay. And then you go through this kind of discussion, and there were 6 points here, each with several terms. And so now you start to ask, is this really a utility function that I want to type into my system? Well, maybe it could be derived from something else. And then this goes back to what was a very, has always been a kind of a popular topic of speculation. It's just like, AlphaZero learned to play chess and Go by playing against itself. Could a math program that's trying to discover math somehow play some game against itself? And that way, you don't have to type in the objective function, or at least do the objective function something very much simpler, and then it infers the rest of it through trying to optimize that. And this is an example of the sort of criterion that you get there. So it's clear that some part of a math game in a multi-agent context is to have one agent state a conjecture and another agent try to prove or disprove it. And then you get this question of, well, how do you favor the right difficulty level? So again, in Mimino, this was based on probability coming out of the language model, which makes a certain amount of sense, but is also kind of ad hoc in my mind. And here's a much less ad hoc thing where if you've played this game, Dixit, the parlor board game, you'll see this idea immediately. You have multiple solving agents, and the goal is now that the agent that proposes the problem is trying to pose a problem which some of the agents can solve, but not all of the agents can solve. And then that's a situation that favors intermediate level problems, but has its own kind of pitfalls. So, but again, something that one could interestingly simulate in a multi-agent context. Okay, so that's my material, these various directions, and I've tried to list here some possible directions that have synergy with work of the other collaborators, and that we could try to work on together. Another one which I didn't mention at all, and again, I'm surprised nobody has really done this, is a deeper analysis of symbolic regression, which again, if you ask for actual AI for science, is a core tool. And there's nothing like the theory that we have for standard numerical, functional analysis and approximation, and that remains to be developed. Broader lessons about, again, I think we should, and it's even incumbent on us to say more about what is the real value of these techniques and what are the lessons for the broader community. This is something that we try to address at our fall workshop, and we'll be running a bit about in our proceedings. Okay, so I'll stop there. And look, thanks for your attention. Look forward to more discussion.
I have a question, actually.
Please,
I wonder, do you have thoughts on like if you want to get AI to sort of learn and discover math on its own,
right?
Like how much is like based on human aesthetic versus sort of objective?
Yeah. That's right. That's so. I definitely, you can debate this, and you'll certainly find many people that say that it's all fashion, and I think that it's almost demonstrably false. But the basic argument that says it is false is to have problems coming from some other direction, like physics. Physics is out there independent of us, and to the extent that our mathematics helps us solve actual problems in physics, it's not just fashion.
But that suggests that maybe the AI needs to like have access to some kind of nature.
Yeah, that's right. In the longer talk, I talk about that quite a bit, that I think a real system, you do have to have like, not a list of problems, but like classes of problems. So like one that I think is very, both was historically very important and I think would be very simple to, base a system on, is just Diophantine equations, so that it's very easy to generate random Diophantine equations. And then the system learns to, figure out which ones it can solve and solve those and figure out which ones it can't solve and so forth. And so, yes, I do think that's actually an essential ingredient. So I'm trying to stop the sharing here. I turned off my that bar, but maybe I'll figure it out. Oh, this is preview. I got to find Zoom to do that.
So I have a question.
Yeah, please. Yeah.
What kind of analysis of symbolic regression do you have in mind in particular?
Well, I've talked about this with people. I mean, the basic, so it would be something which tries to accomplish the same goals as functional analysis, where you say, I have such and such a class of functions, which is usually defined by some norms, that, like the derivatives of the functions are within some, and now I want to show that, such and such, other class of functions can approximate it, again, within some norm, within some epsilon, and then you can ask the same thing here, suppose I, have, this class of functions that comes out of quantum field theory amplitudes or, this other, thing, well, how big a symbolic regression problem do I, need, again, it's not a basis, but it would be like the complexity of the expressions that the things are going to consider to be guaranteed to approximate any such function. And then as far as the difficulty of finding the problem is that symbolic regression is basically NP hard, but then you start looking for structure in the problem to try to figure out. But basically that to say, how big a by direct analogy, except, for replacing how big a basis do I need with, how big an expression do I need?
I see. Yeah. Thank you.
Are there any more questions? Well, if not, let me thank Mike. It was a very interesting talk, and I'll stop the recording here.